Hello and good morning everyone, we are Akilov, Daniyal and
Zhetpis,
and today we are presenting our assignment for calculus, and the title of our presentation is Volumes of Solids of Revolution and Application of Derivative in AI Engineering. We will be exploring how the fundamental concepts of calculus are not just abstract mathematical theories, but powerful application in modern technology, particularly in the field of artificial intelligence. Okay, let's move to the next slide and let's take a quick look at what we will be covering today. As outlined on our slide, our presentation is structured into three main parts. First, we will explain the washer method for finding the volume of a solid of revolution. Second, we will delve into the shell method, which is an alternative approach to solving similar problems. And the third, to connect this concept to our professional field, we will explore applications of derivative in AI engineering.
Thank you, Daniel. So, our first topic is a washer method. What exactly is a washer method? You can think of it's a way of calculating the volume of a solid that has a hollow center, much like a washer or donut. The core idea is that when we rotate the area between two curves around an axis, we get this hollow shape. As our slide shows, the outer curve defines the outer radius Rx and the inner curve defines the inner radius Rx. When we take a cross-section perpendicular to the axis of rotation, we get an annulus, a ring. By integrating the area of these rings along the axis, we can find the total value. This is represented by formula you see here. The key takeaway is that we are subtracting the inner hollow part from the outer solid part. This isn't just a textbook exercise, it has significant real-world connection, for instance in the design of optical lenses for LiDAR systems, which are crucial for autonomous vehicles and the computer vision. The precise volume of the lens is critical for calculating its weight and the optical properties. The shape of a lens is often a curve of revolution. Our example demonstrates this beautifully. We are tasked with the finding of the volume of the solid formed by rotating the region between the curves f of x equals the square root of x and the g of x equals x squared around the x-axis from x equals 0 to x equals 1. We have verified the intersection points and now we are ready to solve it. So let's solve this step by step. Step 1 is the most crucial, identifying the outer and the inner radii. As you can see from the graph, is the upper curve f of x equal root x forms the outer radius of x. The lower curve g of x equals x squared forms the inner radius of r of x. In the step 2, we set up our definite integral. We substitute our values into the general formula, giving us v equals p times the integral from 0 to 1 root of x squared minus x to the 4 dx. This simplifies nicely to p times the integral from 0 to 1 of x minus x to the 4th dx. We will now complete the integration. In the step 3, we integrate term by term. The integral of x is squared over 2 and the integral of x to the 4th is x to the 5th over 5. We evaluate this from 0 to 1. This gives us p times 1 half minus 1 fifth minus 0. In the step 4, we simplify the result, and 1 half minus 1 fifth equals 3 tenths, so our final answer is v equals 3p over 10 cubic units, which is approximately 0.942 cubic units. As you can see, the resulting solid is a model of the glass volume in a B-convex lens. This perfectly demonstrates how the washer method is used in designing real-world AI components like camera systems, and that concludes our explanation of the washer method. We will now hand it over to Daniyal, who will explain the shell method.
So, thank you Rayit. We are now moving on to the second major concept, the shell method. What is the shell method? It offers a different perspective. Instead of stacking flat washers perpendicular to the axis, we can think of wrapping the solid in thin, hollow cylindrical shells. As the slide shows, each shell has a radius of x and a height of f at x. By unwrapping one of these shells, we see it's essentially a rectangular strip of thickness dx. The volume of one shell is approximately its circumference, 2p multiplied by x. It means that time its height to f at x times its thickness dx. This method is particularly useful when rotating around the y-axis, as it often simplifies the integration and avoids solving for x in terms of y. The general formula is, like shows in the slide, is volume is equals to 2p multiplied by integral of x multiplied by f at x and multiplied by d at x. Again, this has a very tangible real-world application. Consider a parabolic microphone membrane used in voice AI systems like Siri or Alexa. To model its material volume, we can use the shell method. The mathematical setup is as follows. We have the region bounded by y is equals to x squared and y is equals to 0 and x is equals to 2. And we rotate this region around the y-axis. Now, why do we choose the shell method here? It's an elegant choice because we were to use the washer method. We would have to solve y is equals to x squared for x, giving us x is equals to root square of y. This would make the integration more complex. The shell method allows us to integrate directly with respect to x, keeping the process much simpler. So let's move to the next slide and let's solve it. Step 1. We identify the components. The shell radius is r, is simply x. The shell height is given by the function, like is equals to x squared, and our limits of integration are from a that is equals to 0 to b that is equals to 2. In step 2, we set up our integral, and it's equals to 2p multiplied by integral from 0 to 2, and in the integral x multiplied by x squared multiplied by dx, which is equals to 2p multiplied by integral from 0 to 2 multiplied by x cubed multiplied by dx. And in step 3 we integrate it, and the integral of x cubed is x in power of 4 over 4. Evaluating this from 0 to 2 gives us 2pi multiplied by 2 power in power of 4 over 4 minus 0, that is equals to 2p multiplied by 16 over 4, and it's equals to 2p multiplied by 4. So, and our final volume is equals to 8p in cubic units, which is about 25.13 cubic units, and this paraboloid shape is exactly the profile used in parabolic microphone dishes, which are critical for capturing directional audio in AI transcription system. This demonstrates how the shell method provides a direct and efficient solution for real-world engineering problems. So now we arrive at the most important section for us as the future AI engineers: derivatives in AI. When you train a neural network by calling model.fit in Python, your computer is silently computing thousands of derivatives every second. This is not a metaphor, it is a pure calculus running on your GPU. The core problem we face is this: a model's intelligence is defined by its weight, that is shows in our slide. And we have a loss function that measures how wrong the model's predictions are. Our goal is to find the set of weights that minimize this loss function. To do this, we use derivatives. Okay, and now let's break down the mathematical foundation. And in the first step, is defining the loss function. For this example, we use the mean squared error, which is the average of the squared differences between predicted y prime and actual y values. Step 2 is computing the gradient, which is the derivative of the loss with respect to the weight, dl over dw. The gradient tells us the slope of the loss function. It points in the direction where the loss increases most rapidly. If the gradient is positive, we need to move left, decrease the weight to lower the loss. If it's negative, we move to right to increase the weight. So step 3 is the update rule, known as gradient descent. We update the weight in the opposite direction of the gradient using a learning rate A to control the step size. Let's solidify this by training a simple AI model by hand, and our setup is simple. One weight, that is W, and the model predicts of y prime is equals y multiplied by x. We have data point of x equals to 2 and the true value that is equals to 6. We start with a random weight, for example 1, and move to the predict and loss. Our model predicts is y prime is equals to 1 multiplied by 2, that is equals to 2. And this is very wrong because the actual loss is 2 minus 6 square, that is equals to 16. So let's compute the gradient, and we compute the derivative. Firstly is dl over dw, that is equals to 2 multiplied by y prime minus y and multiplied by x, that is equals to minus 16. And the gradient is negative, which tells us to increase w. So we should update weight, and we set our learning rate, that is a equals to 0.1, and apply the update rule. So w new is equals to 1 minus 0.1 multiplied by minus 16, which is equals to 2.6. And after just one step, our weight is closer to the correct value of 3. And after enough iterations, the weight will converge to 3, making our prediction perfect. This is the engine of AI, gradient descent. Again, this has a very tangible real-world application. Consider a parabolic microphone membrane used in voice AI systems like Siri or Alexa. To model its material volume, we can use the shell method. The mathematical setup is as follows. We have the region bounded by y is equals to x squared and y is equals to 0 and x is equals to 2. And we rotate this region around y-axis. Now, why do we choose the shell method here? It's an elegant choice because we were to use the washer method. We would have to solve y is equals to x squared for x, giving us x is equals to root square of y. This would make the integration more complex. The shell method allows us to integrate directly with respect to x, keeping the process much simpler.
This brings us to why this matters. Derivatives are everywhere in AI engineering. In neural networks, backpropagation uses chain rule of derivatives to update the millions of weights across the deep architectures. Advanced optimizers like ADAMS, CGT, and the RMS probe are all just sophisticated variants of gradient descent, all relying on first-order derivatives. Even the massive large language models like GPT are trained using derivatives across the billions of parameters to minimize the prediction error on massive datasets. In fact, we can confidently say that without derivatives, there is no machine learning. Calculus isn't just a foundation of AI, it is the core engine that powers an AI. To conclude, let's summarize our takeaways. We explored the washer method, which is used to find the volume of hollow solids via annular cross-sections. With our optical lens, we example wielding V equals 3p over 10. We then examine the shell method, which calculates volume via concentric cylindrical shells. With our microphone membrane, with example giving V equals 8p. Finally, and most importantly, we saw how derivatives are the foundational engine of modern machine learning through the gradient descent. Thank you.